Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure. Hi, everybody. Welcome back to Bufnagle the podcast, where we talk about all things good, the pursuit of the adventure of life. I'm Zach, and since it went so well last time, we might as well go back to the number line again and see where it takes us this time. So that's what we're doing today. Until then, and as always, I'm joined by Rafe. So Rafe, how are you doing today?
Zach, I'm great. Yeah, last week we went off. What do they say? Off the rail, and now we're going to try to get it back on and working. So we're gonna get back on the number line and see if we can take it where it needs to go. But hey, before we get there, I want to say thank you to all our listeners. We're appreciative that you are here. We are a global top 10% podcast. We are reachable at bufnagle@bufnagle.com, Apple Podcasts, Spotify, Amazon Music. There's all sorts of places we're out there. Zach, the other day I was setting up my new printer here. Okay. And so I hook up my printer to my computer and you try to print something, you get all the settings and things like that. And they say, print the test page. All right. So I hit the test page and out comes this piece of paper and it's got like some little, graphic on it to show this and has your IP address and all this other thing. And right at the bottom of the test page, it said, listen to the buff. Zach, we are absolutely everywhere out there. So if you can't find us, let us know and we will get to where you need us to be. If you are new to our podcast, hey, welcome. We are glad you are here. Give us 4 episodes and see if we don't give you something a reason to come back for more. Tell a friend to listen and you will get a free episode. And remember, subscribe and give us a 5-star review. And Zach, what happens? I get pudding and
I get some brownies.
Brownies. All right. That is a great thing. Think of all the good you're doing by that. I mean, you could give blood or you could listen to the buff or you could do both. All right. So,
and then you do both and you get like candy afterwards.
You do get candy when you give blood. Let me do that as a thing. Blood supplies are short. Go give some blood, all right? You got blood inside you. You'll make more. What did they say about Doritos? They said, go ahead and eat all you want. We'll make more. Wasn't that the slogan?
I have no idea, but that's a good slogan.
That was their slogan, is that eat all you want, we'll make more. And so your body will make more blood. So go give some blood and help out somebody in need. Zach, we are talking about infinity, or we're on our way there. And once we get there, we're going to go there and beyond. How about that?
Yeah. So last time we started this topic, and then we kind of just little derailment, and we ended up not talking about it. But we're back. We're gonna try it again, and we're gonna kind of pick off where we left off with the number related discussion of the topic, not the pursuit of doing hard things and finding joy in maybe the mundanity that is life. But,
nice.
Mundanity and numbers kind of go together. So we might as well just tie it all with a nice little bow on top and give yourself a nice little Christmas present here.
In early spring.
Numbers.
Right? Yeah. Okay, so we're talking about numbers. Okay, we're talking about how big infinity is. And this question has come up, and it comes up when I'm a mathematician and other people are not, and they talk about how big is infinity. And I talked last time, Zach, we talked about the shepherd. It doesn't really need to know how to count the sheep, right? All you do is you put the rocks in the bag when the sheep come out of the sheep hut, all right? And then when they come in from the pasture to go back into the cave or the sheep hut, wherever you keep sheep, and you do the inverse thing. And if you got stones left in the bag, then you have to go find some sheep. All right. So that's this process of 1-to-1, and mathematicians use that all the time, this 1-to-1 thing. And it's interesting because there's 2 different kinds of numbers that are out there, and most people don't recognize that there are 2 different kinds. And they seem like they're the same thing, and that is because you are raised in modern times. There's numbers that you use. Well, I guess I'll call them. They're the cardinal numbers. They're the size of a thing. All right. So when if me and Zach in a room, that's 2. There are 2 of us. All right. But if Zach comes in and then I come in, Zach is the first one in the room, and then I'm the second one in the room. Right. So you have cardinal numbers, which are counting numbers, or you have cardinal numbers, which are size numbers. And then you have the ordinal numbers, which represent sequence. right? So there's a first number, and there's a second number, and a third number, right? And then there's the size of the set. And those seem like they're the same thing, but they're really not.
Yeah, I mean, all of this stuff together, if this sounds a little complicated, if you are familiar with sports statistics like I am, you have counting numbers and you have counting stats. Like there were 7 number of passes thrown by Rafe in last game. But you can also sequence on the first pass he did X, on the second pass he did Y. So there's these similar things that are very important with counting, numeralization, and all these other things that apply to our daily life today. It's the same thing with, if you're driving a car, you're the first car on the road, or maybe you're the second car on the road, but you drove X number of miles. At mile 7, something happened. It's these type of things are important in understanding like our place in life and what we're doing and how it helps us, or and sometimes it could not help us, but
they're different kinds of numbers, and it doesn't seem like you're like, well, Zach said the first car and the second car, but that makes 2 cars, and you know what? Yes, it does. All right, and that's exactly the point. Is that the ordinal numbers and the cardinal numbers are related. Okay, and this was a big advance in civilization from a mathematical point of view. Is that okay? Here's the thing: the size of a set is called its cardinality. So if you have 3 things in a set, that set has cardinality of 3, right? But the intellectual advance is that if you start enumerating the elements in the set, there's a first element and a second element and a third element, right? And the great leap was that the cardinality of the set is equal to the ordinal value of the last item in the set. So the cardinality is equal to the ordinal value of the last element in the set. And that's kind of an interesting thing, because as long as you can put them in sequence, you know the size by looking at the ordinal value of the last one. Okay. Now we're going to come back to that in a second, but that's a thing that ties measurement and counting. It ties them together. Okay. So primitive man's doing all this stuff. They're doing a lot of one-to-one thing. We talked about putting rocks in clay jars and breaking the jars and writing on the jars and making symbols. But now we're going to get to some fun things, which is the actual number line.
Yeah. And primitive man, you know what they were also doing? They were also making cave paintings, and cave paintings are cool. But like, I might derail the conversation here, and we might talk about cave paintings for the next 30 minutes. But
that is the thing, and I wanted to look at. And there are cave paintings, and I guess there's evidence of man's. Maybe it might be graffiti. It might be more than just graffiti, but man's reaching outside of himself to alter the world around him to make it more to his liking or to reflect his mind at the time. No.
Yeah, I mean, additionally, too, like, if you think about it, primitive man, they didn't have language written language. They had verbal language, obviously. I mean, it might have just been grunting and poking and things like that. But the idea of being able to draw a picture and paint a story that way is, again, a very, very human expression. And it's one of the first human expressions. Last week I mentioned how, like, math is one of the first academic expressions of humanity, and painting pictures and storytelling is the first, like, maybe I'm going to say it's the first human expression of life. It's doing that thing. It's showing, hey, this is the story. This is the trip I want. This is me and my buddies. We went hunting and we saw a saber-toothed tiger and it killed Joe, or something crazy like that. Or this is me running away from the bear. You can see I ran it away because I'm not the slow one. Like,
right, I made it back.
And I'm telling the story.
I told the story, so I'm the guy who made it back. And there's some what statisticians call that selection bias, Zach. All right, the things that made the people who made it out were able to tell the story. It's a fascinating I guess I'll call it the history of man's development of man. Becoming something other than just an animal in the wild. That's what part of this math stuff is. So we got these ordinal numbers that represent the cardinality of sets, right? And what we do is we eventually put them on a number line, all right? We've done that, and most of the time we go number line left to right. We put a 1 and a 2 and a 3, and we put little tick marks on the line. And I remember you remember when you first heard the number line, Zach? Do you remember when you first saw that?
Probably I was 2, and you gave it to me as like birthday present or something.
Yeah, it was probably your Christmas presents came wrapped in mathematical wrapping paper, I'm sure. Well,
I don't think my mother would allow that, but they didn't match the theme. She got mad at me because I wanted to get wrapping paper that had like an avocado dressed up as like all Christmas avocado, and she said, "No, we can't do that because it doesn't match the theme." I'm like, really? The theme is Christmas, fun and happiness, and it matches the theme of fun and happiness.
No, I hear you. I'm a big fan of like, I had friends that there was kind of a common thing in the 70s to wrap presents in the comic sections from the newspapers.
Well, that's back when we had newspapers. So,
and if you used the Sunday section, it was really colorful and kind of cool. So, all right. So I remember the number line, and I remember thinking, this is kind of stupid. It's like, I just know the numbers. How come I can't remember them? And other people had problems with the number line, basically because they had trouble remembering the numbers 1 to 10. But eventually you get to that. Okay, you put the numbers, you put them on a line, and you draw one out horizontally. But then the great advance came from a guy named Descartes, Zach, and he figured out that you could put two number lines orthogonal to each other in 90 degrees, and we have what we call the Cartesian plane now after Descartes. All right, and we have what we'll call the x's on the horizontal direction. We got the y's in the vertical direction. All right, and now you have a plane, and you can do some really radical stuff. You can do functions, and you can do relations between x's and y's. Okay, so the question is, when you start doing that, when you start drawing the number line, I remember saying to myself, and then to the teacher, how far do I go with the number line? 1, 2, 3. I mean, I can keep going. Is there a way? How far does this number line go? I would ask that question. And they said it goes all the way to infinity. And I said, well, what does that mean? And she said, well, when you're older, you'll listen to the podcast and they'll tell you what that means. Okay. So
nice.
Yeah.
I see what you did there.
Yeah. So that's kind of like, yeah, that's what I did there. Okay, so
that's like the time travel experiment where like you go back and like you're your own grandfather, or you kill your mom, and then you're not. It's it's the same thing. It's like your teacher's like from the future who tells you about the podcast to do the thing.
It's like Bill and Ted saying, "Well, we haven't invented it yet. We haven't invented the time machine yet, but let's just go into the future where we have the time machine, and then tell our future self how to build it." Right. So it's all time travel. Right? We did a time travel thing, and then
we mentioned time travel. We haven't done a time travel thing. I mean, we could derail this conversation and go into it.
Like the first or second podcast, or maybe that's on the missing episode.
No, I don't think it's on the missing episode, but I do believe we have mentioned time travel. We talked about the show Dark, which is a time travel related TV show. We have not explored the concept of time travel as an episode.
Well, write that one down because that may be coming. All right, what do they say? Bookmark this page.
Something like that.
Did they say that? Okay.
All right. So the thing you'd say.
Okay, so infinity's this thing, and kids use infinity all the time when they're like in early grade school. They use it like as a the world's biggest trump card. It's the take all trump card. It was like, I was here first. No, I was here first. No, I was here first. No, I was here first. Infinity. All right, and then it's like that somehow that's like you're at the end and you can't get past it. So that's how they use infinity. Okay, but that's not quite what infinity is. Did you ever do that, Zach?
I did, and then you got mad at me because I was using infinity wrong. I was 7.
All right,
poor 7-year-old me.
All right, I think
there's to deal with.
I think there's essentially I'll call it like 3 different ways to think about infinity. Okay, all right, and the first way I'm going to think about infinity is as the input to a function. Is something you throw into a function. All right, and then we look at what happens. Okay, so a function is we also talked about, we had a function machine when I was like in 5th grade. Okay, they called it a function machine. It was like it's a sketch, and you take a number, you drop the number into the hopper at the top, and you turn the crank, and another number comes out the side. Now it could be the same number. It could be that number squared. It could be that number plus 10. Who knows what it is, all right? And I remember one time somebody set the function machine to divide by whatever number you drop in there. Take 1 divided by the thing, and somebody dropped 0 into the function machine, and it broke, right? Because you can't divide by 0, right? So and I remember this little sketch in the math book. There were these people sent, and it looked like a machine, Zach. Okay, it was like your typical industrial looking machine from the 70s. It had a big hopper on the top, and these guys standing around in hard hats and stuff, and a big crank on the side, and like gears. And
so is that why you thought math was going to be a lot like construction? Is that why you got into math? Or?
Well, yeah, because that way I could, like, if you're doing math, it's the same as watching like the dump truck come by, all right? So they're standing there, and the machine is all broken. Okay, there's smoke coming out of it, and there's like springs and gears flying all over. And one guy comes up to the other guy and says, "What happened to the function machine?" And he said, "Somebody tried to divide by 0." And as you can see, that had a dramatic effect on my young mind because, in fourth grade or whatever that was, when we started doing functions, that I don't set the function machine to divide by 0. That's going to be a problem. Okay, so let's say you got
How
a
do you
function.
fix the function machine once you've broken it, though?
Well, see, that's the great thing about the function machine is the function machine is there really is no function machine, right? It's just this conceptual idea in your head, and it's one of these. The function machine is a great intellectual leap, like the ordinality cardinality thing, like drawing cave paintings, like all of that stuff. The function machine is really important. Well, you have to look, if you look at the history of mathematics through the Middle Ages and into the 1700s, the concept of the function becomes really, really important. And I don't think like Laplace and Cauchy and Descartes and those guys always talked about function machines the way I do, but it's taken us a while to get there. But functions were really, really important.
Yeah, that's okay. I mean, I'm not going to argue with that. It's just
Okay, so the first way to think about infinity is as the input to a function. Okay, so here's the idea, Zach. Let's say I have a function that is x plus 1 over x. All right, x plus 1 over x. So I'm going to give you an x, and you're going to give me back x plus 1 over x. So if I give you 1, you give me 1 plus 1 over 1, which is 2 over 1, which is
2.
Right, okay. And if I give you 2, you give me back 2 plus 1.
2 plus 1 over 2.
Which is?
3 over 2.
Which is 3 halves, okay? And if I give you...
1.5.
Yeah, 1.5. And if I give you 10, you give me 1.1. And if I give you 1,000, you give me 1.001. And if I give you 1,000,000, you give me 1.00000 6 zeros and a 1, okay? So what's happening is I give you bigger and bigger numbers. And what maybe they're really big. You got to use 2 hands to hold them, right? I gave you really, really big numbers, and you're giving me numbers that are closer and closer and closer to 1. Okay? So I can ask the question, what if I give you like really, really gigantic numbers? What's happening to the number you're giving me? And the answer is you're going to eventually give me something really, really close to 1, right? So yeah. I give you essentially something that's infinity, and then you're going to give me something that's essentially close to 1. But you're never going to give me 1, are you? You're giving me x plus 1 over x. Okay, so there's this concept that hit the mathematicians in the early 1800s. And there was this guy named Cauchy, Cauchy, right? And he defined this concept that we are talking about now, which is the concept of a limit. Okay, so what is the limiting behavior of x plus 1 over x as x gets really big, as x goes to infinity with the finger
As x gets really, really big, your output gets closer and closer to 1.
Right. So, but the infinity question is, because I can't give you infinity. I can't, I could write that down, but that won't fit in the hopper. Okay. So the question is, how do I think about this concept of infinity? Okay. So when we talk about infinity in that sense, as the input to this limit, okay, we're saying that, all right, I'm going to say that the limit of x plus 1 over x, as x goes to infinity, that limit is 1. And what that means is, however close you want me to get to 1, I can get there by going far enough out with x. Right? I can get x plus 1 over x as close to 1 as you want if I go far enough out. So you might tell me, well, I would like you to be within 0.001 of 1. I would like you to be that close. I would say, well, okay. And I do a little computation and say, as long as the x I dropped into the machine, as long as that's greater than 1,000, then the output will be within 0.001 of 1. Right? If I want to be within 1,000,000 of 1, then I got to go out past 1,000,000. Right? So no matter what you give me, I can give you a value beyond which that function will be that close. Okay, that's the limit. Okay, and when we talk about going to infinity, we mean there's a point at which you can get as close as you want. There's a point past which you can get as close as you want. And since I have a zillion numbers, I can just keep going out there as far as I need. I'll be okay. That function has a limit there at 1 as x goes to infinity. Okay, so that's the sense of infinity as the input to a function. Okay, now not all functions have limits. Okay. If I take f of x equal to x, and I keep dropping in different bigger x's, then the outcome just gets bigger and bigger and bigger anyway. Okay. So now, here's another function, Zach. what if I take the function f of x equals 1 divided by x? Right? I take 1 divided by x, and I let x get closer and closer to 0. This is like getting ready to blow up the function machine, okay? So I take a number at like a half, and I drop it in, and you'll give me
2.
Right. And I take in 1 over 10, you will give me
10.
All right. Okay. And 1 over a million, you'll give me
1 million.
Right. Okay. So if I want that, so as the input gets closer and closer to 0, the output gets bigger and bigger and bigger and bigger. Okay. And there's no limit there on the output. All right. If I would like, and what I mean by no limit is I can make the output as big as I want by making that input being as small as it needs to be. Okay. So we say that there is no limit to 1 over x as x goes down along the positive numbers towards 0, because I can always exceed any value. You want me to be bigger than 10 bajillion, Zach? Then I'll put 1 over 10 bajillion into the machine, boom, and I'll exceed that. Right?
Yep.
So
or it's 10 bajillion plus 1.
Right. I can always get bigger. Okay. So that's the concept of infinity as the output from a function. All right. So, and you can think of, like I talked about, f of x equals x. Like there's an infinity you can drop in and an infinity you're going to get out. That one just doesn't behave very well when x goes out to the edges. Right. So now the question is, how big is that infinity? Okay. And that's going to bring us back to infinity as the size of a set. Okay. So remember, we talked about the cardinality of a set is the ordinal value of the last element when you list them out. All right. So if I got a set that has x, y, and z in it, x is the first one, y is the second one, z is the third one, z is the last one. So therefore the cardinality must be 3. Okay. But what if I have the natural numbers, right? The numbers that are used for counting. Those are the natural numbers, Zach. You talked about that last week. They're the ones that
your 2s, your 3s,
Yeah.
your alphas. Wait, that's an alpha.
No, yeah, that's not a number. That's a letter. But if you have your natural numbers, how many of them are there? How do we talk about the cardinality of that one? Because what's the ordinal value of the last element in that set? Well, there's no last element. So what's its cardinality? All right. So what we're going to do is we're going to say, well, we're going to say it has a cardinality. All right. And we're going to use its cardinality, whatever it is, we're going to use that to measure cardinalities of other sets. Okay. Now, the natural numbers are said to be countably infinite, which means you can count the natural numbers. You can say, here's the first one, here's the second one, here's the third one. You can do that with the natural numbers, right? In fact, it's pretty obvious that the first one is 1, and the second one is 2, and the third one is 3. So you can count them, okay? So the cardinality of the set of natural numbers is called aleph-null. You ever heard that, Zach? Aleph?
No, that sounds made up, though.
It sounds made up, but it's just like
but
that.
You know what else is made up? Math is made up,
Math?
so it's okay.
You know, it all just comes out of your head, Zach. All this comes out of people's heads. So aleph is a Hebrew letter, and it looks kind of like a squiggly capital N. So it fits well here. And null means like 0. It's like it's the starting point. Okay. So like the smallest kind of infinity is aleph-null, and it's the cardinality of the set of natural numbers. Okay. So I got a set 1, 2, 3, 4, 5, 6, 7, all the way up. It's got a cardinality of aleph-null. So here's the question. Let's take another set, right? Let's take the natural numbers, and we're going to add 0 to that set. So now we have a set that has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way. What's the cardinality of that set?
A lot.
It is a lot. It is a lot. Right? So you would think to yourself, well, it seems to me that it ought to be a little bit bigger than the natural numbers because it's got a thing in it that the other one doesn't have. But the question of size has to do with ordinality, right? And how it relates to cardinality. So I can take all the numbers in the set 0, 1, 2, 3, 4, 0 outward, and I can match them up 1 to 1. Remember the 1 to 1? I'm going to match them up 1 to 1 with the natural numbers. Okay. The first element in the set 0, 1, right, starting with 0, the first element is 0. The second element is 1. The third element is 2. The fourth element is 3. The fifth element is 4. All right. So I can enumerate all those elements in that set, and I get them to match up 1 to 1 with the natural number. So the set that includes 1, 2, 3, 4 out to infinity and the set that includes 0, 1, 2, 3, 4 out to infinity, those sets have the same cardinality. They are of the same size. Even though that looks like there's an element in the second set that's not in the first one.
Impressive.
Yeah, that's a thing that that kind of blows you away. So if I take the natural numbers and the non-negative integers, they have the same cardinality. They have the same kind of infinity. That's kind of fun.
If you're a math nerd.
Okay, so let me ask you this question. Okay, so what if I take the numbers from minus infinity? What if I take all the integers from minus infinity to plus infinity? All right,
it's a lot of integers.
There's a lot of integers, okay, and you need a big.
That's an infinite amount of integers. See what I did there?
Yeah, but the question is, what's the cardinality of that set? You start with 0. Remember, we said we start with 1, 2, 3, 4, 5, 6, 7, that set, and the set where you add 0. But now I'm adding an infinite number of other elements in there. What's the cardinality of that set? Well, it turns out it's the same. It's the same. Because what I can do is I can enumerate that set as well. I can say 0, -1, +1, -2, +2, -3, +3. And I can match them 1 to 1 with the natural numbers. Right?
That's what I was going to say you should do.
That's exactly what you were going to do. That's what you were
I have good ideas on occasion.
Okay, so let me ask you this question. Okay, so we'll make the set a little smaller. Instead of taking that set, let's take the set of the positive even integers.
So 2s, 4s, 6, 8.
Yeah, we got your 2s, you got your 4s, you got your 6s. Okay.
You got your Lemonheads, you got your Grapeheads.
Okay, so there was this coach. Sidebar. All right, so there was this coach.
Wait, we've never done this before.
Was that football? Is that college football?
Yeah.
High school football?
So college football.
Yeah, you didn't do that. Okay, so this was and this guy was a very fun guy. And one day we were standing around talking after practice, and he was eating. What was he eating?
He was eating Lemonheads.
No, but he was eating like when I was a kid, you could eat the Lemonhead candy, right?
Yeah.
All right, but he was eating like something other than Lemonheads.
Heads and Friends.
Lemonheads and Friends, that's what it was. And you can get like, he was very excited about the different kinds of friends that the Lemonheads had. All right, and he explained to us that you got your Lemonheads, you got your cherry heads, you got your grape heads, you got your orange heads. All right, so you got your even numbers, okay? You got your 2s, you got your 4s, you got your 6s. All right, so what's the cardinality of the even numbers? It seems like it might be half of what the natural numbers are, right? Because there's odds and evens in there.
It's half of your biggest number that's in that set. If you started at 2. So 2, 4, 6, half of 6 is 3.
Right. So you can still enumerate them, right? So 2 is the first one, 4 is the second one, 6 is the third one. So they have the cardinality of the even numbers is the same as the cardinality of the natural numbers. And the same thing goes for the odd numbers. Okay. So that gets kind of complicated. Remember, these are all countably infinite sets. Okay, so now what about this? Okay, so that's, I can see what you would say, I can see what you did there. You kind of dropped one guy in there and shifted everything over, or you kind of shifted everything out by a factor of 2 or 3 or something like that. Okay, what if you do this? What if you looked at all the rational numbers? All right, the
numbers are rational?
The positive rational numbers. Okay, so those are numbers that when you take like P over Q, and P is an integer and Q is an integer. Okay, it's like 2/3. Okay, we were doing the integers before, but now we're going to look at all, like when you take the ratio of the integers. What about that set?
Great question. Good thing I'm not a mathematician because I don't know the answer.
The question. Okay, so here's what you do. All right, you're going to make a grid. Okay, and across the columns, you're going to write 1, 2, 3, 4. You're going to list them all across the columns that way. And then down the rows, you're going to write 1, 2, 3 down the rows that way. And the column thing is going to be the denominator, and the row header is going to be the numerator. So the first row, first column, you get 1 over 1, which is 1. First row, second column, you're going to get 1 over 2. Third column, you get 1 over 3. So those are all the 1 overs. Okay. The next row is going to be all the 2 overs. You're going to get 2 over 1, 2 over 2, 2 over 3. You're going to get all of them. So you can see you can list in that grid. You can list all of the positive rational numbers. You can see them in there. Now, there's some repeats, right? 1 over 1 and 2 over 2 and 3 over 3, those are all the same number, right? And 1 over 2 and 2 over 4, those are the same number. But here's what you do. You start in that upper corner with 1 over 1. And then you snake back and forth diagonally across the grid. So you start at 1 over 1, then you go to 1 over 2, then you go to 2 over 1, then you go to 3 over 1, and 2 over 2, and 1 over 3, right? You see, you snake back and forth across that. And whenever you run into a repeat, you just throw it out. Okay? And what you get then is you get an enumeration and a sequencing of the rational numbers that is 1-to-1 with the natural numbers. So the positive rationals must have the same cardinality as the counting numbers, as the natural numbers. What do you think of that?
Pretty fancy.
Okay, so those are all those. Okay, and then obviously, I bet you. I'll leave this for an exercise for the reader. All right, I'll bet you can demonstrate that the negative rationals have the same cardinality. Okay, so we got the counting numbers, or the natural numbers, the counting numbers, integers, rationals. They all have they're all 1-to-1. All right. Are there any other cardinalities? All right, and the answer is yes. Okay. There are bigger numbers of infinities. Okay. So here's how you get there. And Zach, this is the last thing we'll do. So then you can rest. This is
hey, this is hard for me to do at 8:34 in the morning.
You're taking all of these breaks here with water and having to get your Gatorade and stuff. And
yeah, I gotta stay hydrated. What do you think? You think I went to school dehydrated?
No, that is the thing now. Oh, kids are always carrying around these,
Yeah, but they're massive water bottles. I'm like, really, dude? Like,
Camelbacks, and yeah, I got you.
It's just have your water, have it available. But like, I'm not even gonna go there because they have their water, but then they have like 3 sodas, coffee, and something else. And it's like,
oh, the kids drinking coffee too, like the middle school kids and the grade school kids drinking coffee is amazing to me. I still don't drink coffee, so that's.
I mean, but you do drink a fair bit of caffeine.
I do drink. I get my caffeine through the sodas, which is fine, I guess.
Which we've proven apparently are healthy.
We have proven that in an old episode. If you go back through the canon of Bufnagle, you can find proof that Diet Mountain Dew is just as healthy as what was it, orange juice?
Smoothies, I think, is what we're
Okay, so here's what we're going to show, that there is an infinity that is bigger than the countable numbers. Okay? There's an infinity that's bigger. Okay, so now remember, a couple podcasts ago, we proved that the square root of 2 was not a rational number. Do you remember that? That was the pudding episode?
Yeah.
That is proving to be quite the interesting episode. But you listen to the pudding one, we will prove to you the square root of 2 is not rational. All right? So we're gonna look at some numbers here. We're going to show you a set that is not countably finite. It's bigger than countably finite. Okay? And we're going to look at all the numbers between 0 and 1. All right? All the numbers that are between 0 and 1. Okay, now, we are going to do a proof by contradiction, right? Which means we're going to assume something, and then we're going to reason from that assumption and find out that we get to something that doesn't make any sense. And since our reasoning was valid, then the assumption must be false. Okay, and we did that for the proof of square root of 2 not being rational. And we're going to do the same thing here. Well, a similar thing. Okay, so now here's the first thing to note, Zach. All right, you know about base 10. That's where you live, right? Base 10.
Yep.
10 fingers.
Well,
10
I live
toes.
on the planet. I live on the Earth.
You live on the Earth. That's right, where you count on the fingers, right, and the toes.
Eventually, I will live on the Mars and do the same thing.
You can do the same thing on Mars because you still will have 10 fingers and 10 toes. But you can do counting in different bases. Okay, when we talked about color, we talked about base 16. All right, we talked about, and there can be base 2. All right, zeros and ones. All right, so 1 is just 1, and 2 is 1 0, and 3 is 1 1, and 4 is 1 0 0. Okay, so that's how you count up. But you can do fractions that way as well. 1/2 is 0.1, right? Because that decimal point holds 2 to the minus 1, and the next one is 2 to the minus 2, right? So 1/4 is 0.01, and 1/8 is 0.001, and 1/16 is 0.0001. Okay, now I'll bet you can convince yourself, and I'll leave this as an exercise to the reader, that every number between 0 and 1 can be written in what's called binary decimal form. All right, so what you can write it as a 0 point some sequence of zeros and ones. You can write it that way. For example, you can write 5/8 is 1/2 plus 1/8, which is 0.101. Okay, and then a bunch of zeros after that because they don't matter. Okay, so I'm gonna hope that you will trust me that every number between 0 and 1 can be written in that binary form. Okay, now, that's a sequence of zeros and ones, and it has a first component, it has a second component, it has a third component, it has a fourth component. In fact, the components match up 1-to-1 with the natural numbers, right? So there's a countably infinite number of decimals there. Okay, is that all right?
Yep.
All right, Zach's still awake. Okay.
This is high level stuff.
Oh, this is pretty high level, and we're doing it auditorily. So if you're driving, you should be writing.
You should probably not be driving.
you can write this like that fog on the window. If it's cold outside, you can do it. You can write it that way, and that way you don't have to use a pencil. Okay, so
a pencil.
So it turns out you can write every number as a sequence of these zeros and ones. All right, so like 1/3 is actually 0.01, 01, 01, 01, 01, all the way out. That's what 1/3 looks like. And your calculator may have, if you have an advanced calculator, it may actually do that for you. Mine will convert to binary for you. Okay, you hit the button, it'll make it binary. Woohoo! Okay, now
you think you're better than us?
All right, so we're going to assume that all those numbers between 0 and 1, that set is countably infinite. That there is a first number, that there's a second number, that there's a third number, that there's a fourth number. Okay, we're going to assume that you could do that you could list them out. I mean, if you had, what do they say? Had we but whirled enough in time, right? If you have enough chalk and a big enough chalkboard, you could list them all out, right? Because it's countably infinite. Okay, so let's say you do that. Okay, you have a first number and you wrote it out. You have a second number, you wrote it out. You have a third number, you wrote it out. So imagine that you stacked them all up on top of each other. So the first number has all its zeros and ones going across. The second number has all its zeros and ones going across, and they're all lined up. Okay, here's what we're going to do. We're going to generate a new number. Okay, a new number. We're going to go to that first row. Okay, and this is a proof that is about 100 years old by a man named George Cantor. Okay, and he developed this proof to show that the numbers between 0 and 1 are not countable. Okay, so you go to the first number, take the first digit of the first number. Okay, if it's a 0, I want it to be 1, and if it's a 1, I want you to take a 0. So you're going to take whatever the first digit of the first number is. I want you to invert it, and I want you to write it down. Okay, now go to the second number and take the second digit in the second number. If it's a 0, write down a 1. If it's a 1, write down a 0. Okay, so now you got 2 digits, right? Go to the third number, which is the third row, and take the third digit of the third number, right? That's either a 0 or a 1. Write it down, flip it over, and write it down, okay? And keep going, okay? You are going to generate a countably infinite sequence of zeros and ones, okay?
Yep.
Okay, it's countable. Okay, now, since it's a countably infinite sequence of zeros and ones, it must, and that represents that decimal representation of a number. That number, that representation is a number between 0 and 1, right? Okay.
It is.
But that number's not in your set, right? I know that number's not in your set because I know it's not the same, because it doesn't match. It's different than the first number because the first digit's different. It's different than the second number because the second digit's different. It's different than the third number because the third digit's different. In fact, it's different than that number you wrote down is different than every other number in that list. It's different than all the numbers in the list. So therefore, it's in the set of zeros and ones, or numbers between 0 and 1, but it's not in the list you wrote down. It's different than that.
So it's a new number.
It's a new number.
You invented a new number.
Well, but I couldn't have invented a new number because I wrote them all down. Okay, so where's my fault? The fault is in the assumption that I can write them all down. Right? There must be more numbers than I can possibly write down in that fashion. Right? That set of numbers must be uncountably infinite. And it's bigger than the set of countably infinite numbers. Okay? Wow. Did you hear that? Zach's head just exploded. Okay? That's a very cool
hard.
thing. This is
why they say math is hard.
Well, let's
go shopping.
This was around 1900. Cantor started playing with these different kinds of infinities. Okay? And this new number here it's a number between 0 and 1, and wasn't listed in the original set. It's in the set, so therefore the set can't be countable, right? And he showed that in fact, you can take all the rational numbers out of the range between 0 and 1. Take all the rational numbers out, and you know what you get? You still get a set uncountably infinite numbers. In fact, you can take all the rational numbers out, and you still have more than enough numbers to work with. It's a stunning thing. Now, remember we talked about aleph-null? That next set is called aleph-1. It's the next set. Okay, and then you're going to do some really wacky things. You can look at the set of all subsets of these sets, and that gets bigger, and and then there's a whole mathematics now that he invented, this whole mathematics of infinities, where you can add and subtract infinities, and you can multiply infinities, and you can do all sorts of wacky stuff, and there's a whole arithmetic that gets around there. So anyway, just realize as you're driving down the road there, taking the kids to school, that you may feel like you're in hell because you're driving because school seems to take forever. But there are bigger infinities than the one you are in, and it just keeps going. That is your introduction to infinities. And
introduction, more like advanced infinity with Bufnagle, the podcast.
Well, that's okay. So you know what? I was talking to you the other day. I said that we watched Jeopardy, and the answers every night of the last week, there's been a question answer, whatever. There's an answer that has a question on Jeopardy that has been answered in one of the Bufnagle episodes that we've done over the last.
So what I'm hearing is, if you listen to us, you will win at Jeopardy.
That's exactly what I'm saying. This thing. Right. So that you just wait.
Out.
I'll bet next week we're going to see a question on George Cantor. I bet that's what it'll be. It is. Well, that's the infinity. Okay, so that's how big infinity is. And think about that when you're working with your, balancing your checkbook with those rational numbers and your decimals. There's a lot of mathematics out there that is very interesting, and you can see why it's difficult to keep your head around these things. These are pretty advanced concepts, and they are very hard.
Yes, they are hard concepts, but they're good concepts for us to explore. So I want to thank all of our listeners for listening. I want to remind you to go seek the good, be the good, and spread the good. Enjoy the adventure of life.